This is Bill. I'm back with Chapter 2 of the CompTIA IT Fundamentals or ITF Plus certification course. This chapter, Chapter 3 and Chapter 4, all are related to computer hardware. And when you finish those 3 chapters, you should have enough knowledge to actually know all the components within a standard computer. And even if you should have an idea of how to even build one from the hardware standpoint after you finish these next 3 chapters. So this chapter is Chapter 2, and we'll be discussing central processing units, memory, that's RAM memory, not hard drive space, motherboards, and power supplies. So remember from our last chapter, there are 4 parts of a computer system. The central processing unit, your input devices, output devices, and storage. Now storage we broke into specifically RAM storage, random access memory, which we'll discuss in this chapter, and hard drives, which will be, again, a future chapter. Your central processing unit is also called a microprocessor or processor, handles all the math or most of the math within a computer system, and makes all the decisions within the computer, what to do with the data, how to do it, where it goes, where it's stored, how it's processed. It's all handled by the CPU. The CPU is manufactured in thin coats of wafers of silicon and transistors. They're packaged into a really hard, durable shell. The 2 biggest manufacturers of CPUs, or central processing units, are Intel and AMD. They make pretty much all of the CPUs used in your laptops, desktops, and servers. ARM makes the CPUs used in Android mobile devices, tablets and phones. Apple designs and manufactures all the central processing units used in its Apple devices. So basically, unless you're using an Apple desktop or laptop, you're probably going to run into an AMD or an Intel processor. Again, Apple has their own. The CPU, it plugs, along with other devices, plugs into a device called a motherboard, and we'll discuss the motherboards a little bit later. But the CPUs plug into that motherboard within the computer system itself. Your CPUs have various specifications that you need to understand. Before I discuss those, some of the specifications, we start discussing the specifications, you got to become familiar with some of this terminology. Kilo, or K, is times 1,000. So 1 kilo of, or 1 kilobyte, or 1 kilobit is 1,000. But 1 kilo is 1,000. So a kilobyte is 1,000 bytes. Mega is 1 million, so a megabyte would be 1,000,000 bytes. Gigabytes is 1 billion, or and it could be gigabytes, or gigabits, gigahertz. So that'd be 1 million. Tera, for example, terabytes would be 1 trillion. Peta, 1 quadrillion, and exa is 1 quintillion. So you'll be using these terms, kilo, mega, giga, tera, quite often within the IT world. PETA is becoming used quite a bit within storage, and I have seen one company that uses exa in terms of storage. But so you will be seeing, again, kilo, mega, giga, and tera quite a bit in your profession. PETA and exa, if you work for larger organizations, those are becoming more common. At least the petabytes are in storage. So let's go back to our CPU specifications. Our CPUs have specifications you have to understand that allow for performance and compatibility. The first one is speed. This is basically how many cycles per second is your CPU going to operate at. So 1 cycle is called 1 hertz. Your modern processors run at gigahertz. Again, let's go down here to that's 1 billion cycles per second. So 1 gigahertz, or GHz, is 1 billion cycles per second. So something comes in to the processor, it can handle 1 billion of these cycles, just processing data very, very, very fast in 1 second. To achieve the proper CPU speed, the CPU must work directly with your motherboard. The motherboard maintains a clock speed measured in hertz for the system. Your CPU runs as a multiple of that motherboard's clock speed. So it might run at 10 times or 25 times the bus speed. If the motherboard has a clock speed of 1000 megahertz and a CPU has a 25 multiplier, the CPU runs at 2.5 gigahertz. And it's just one quick example. Other specifications of your CPU are 64-bit computing, multi-core CPUs. This is where we take a single processor and we basically take a second CPU and bundle it into the same packaging, and we call that a multi-core CPU. Program handling and cache. Another CPU specification is our 64-bit computing. From 1985 to 2001, the most common processor was the 32-bit CPU. In 2001, Intel decided to manufacture the 64-bit processor. To give an example of what a big significant improvement this was, the 32-bit processor could access 32 bits of data at a time, while the 64-bit processor can handle 64 bits of data at a time. So basically double the amount of data can be processed per second by the CPU. It also gave us more memory that we could address. The 32-bit CPU could address 4 gigabytes of memory. The 64-bit can access up to 16 exabytes. However, most systems today are designed to handle a lot less than that, usually under a terabyte. Your desktops are even less than that, but you will see systems running quite comfortably today in the 8 gigabyte, 16 gigabyte range for laptops, as an example. Servers, you will see up into hundreds of gigabytes of memory, but again, that's all due to the 64-bit capability of our CPU. Prior to the 64-bit, we were limited to 44 gigabytes of memory. A multi-core CPU is basically we're taking a single CPU chip and we're adding multiple of those CPU chips onto one giant chip. So we're taking one CPU, we're taking multiple CPUs, combining them on one giant chip, and that is our new central processor. So that is a multi-core CPU. So each CPU chip is called a core, and we take multiple of those cores and we put them all into one big huge enclosure and call that the CPU. The advantage of multi-core processors is each core can process data independently, or cores can actually use to load balance the system out. So if one core gets busy, it can ask or offload processes to another core. And we get those, that does help in terms of performance. If one core gets busy and it's running, say, 100% utilization and more data needs to come in, it can offload that to a second one. So again, the other option is some processes are handled by one core and other processes can be handled by another core. So again, we have that load balancing capability. Multi-core CPUs are noted by their cores that are integrated into the package. So a dual-core CPU has 2 CPUs within it. A quad-core has 4 CPUs. Intel makes 24 core CPUs that can be used in real powerful desktops, and in your most powerful servers today, we have 144 core CPUs that can be purchased. A CPU has a set of commands that they understand, and these commands are called the instruction set or code book. This is at the machine level system. These are very cryptic commands. You wouldn't, unless you took a class in assembly language, you wouldn't even know what these commands look like. They're, JSR, JMP, they're a bunch of weird commands at that machine code level. Cache is a very small amount of RAM that's actually installed on the CPU chip itself. This RAM is used to augment and make the CPU faster when it comes to addressing memory. When you go out and buy a laptop or a desktop, it might come with 8 or 16 gigabytes of RAM, and the CPU can directly address that RAM, but that RAM is relatively slow compared to the CPU. So what manufacturers have done is they take a small amount of RAM, they install very, very fast RAM and install that on the CPU itself. So when the CPU goes out there to address RAM and it needs to pull data from RAM, it grabs that RAM in the slower memory, the 8 or 16 gigabytes of RAM. It pulls it in and it copies that data to the cache. So as the CPU is processing, the first thing it does when it needs that data again, it looks at cache, which is very fast, and it can grab that data, modify it, and then save it back out. And again, it goes to cache, and then there's another process that will take it out to a RAM memory if necessary. There are two types of cache. Level 1, that's your smallest and fastest. This is checked first. Then level 2 and level 3, or L2 and L3, it's larger than level 1, it's slower, and it's checked after level 1. If data is not found in the cache CPU, then the system will go out to the slowest RAM, that 8 or 16 gigabytes of RAM, and check that for data. As our CPUs get faster and bigger and more powerful, they need a lot more cooling. They need to be cooled down. You don't want them to. They can't get hot enough right now where they can actually burn. So manufacturers need to develop systems that can cool our computers down. We don't want these things getting so hot that they melt. So manufacturers developed two types of ways to cool a system. One is called active cooling and one's called passive cooling. Passive cooling doesn't use power or mechanical parts. The most common form of passive cooling is a heat sink. This is a large chunk of metal with fins that is glued with a heat conducting glue that is glued right onto the CPU. That glue and the heat sink will draw heat away from the CPU, effectively cooling it. An active cooling uses electrical power and parts such as fans to cool a computer. The most common is a cooling fan. The fan might be installed on top of the heat sink, and it's a fan. It's sucking air away from the heat sink into the chassis itself. In addition to that, we might have additional case fans that can be part of the power supply, or a separate fan assembly that will blow air out of the system to get the hot air out of the computer system itself. The third type of cooling we encounter, and you'll find these on real high-end gaming systems or real high-end servers that do a lot of processing, a lot of very complex operations, is a liquid-cooled system. In a liquid-cooled system, there is an internal tube that is sealed and that will carry a liquid throughout the computer system. So that tube will again come in contact with the CPU and other critical components, and it is circulated through the system. It is actually circulated even outside the computer system, so it actually cools, and it's liquid cooling within the system itself. Now, random access memory, or RAM, is a short-term storage. RAM holds information that you're currently working on. It's that spreadsheet you're working on. It's the PowerPoint you're working on. It's the Word document. It's your browser. It's the stuff you're actually currently working on. The CPU is actually processing that and accessing it, accessing that data relatively quickly. It is temporary storage. So once your data is finished and saved, once the application closes, you're finished with your Word document, you close the document, that data is gone. If you lose power to the system, that data is gone. So it is fast, but it's also temporary. So you want to make sure that you save your data often, because if you lose power, it's gone. It's just not meant for long-term storage. It is technically it is a temporary storage system. RAM is not sequential. Some systems are sequential, where data is accessed in sequence. Here's 1, 2, 3. We'll say you need to access the 10th one in the line. It's got to load up 1 through 9 before it gets to 10. RAM is not sequential, it's random. If you need data at point 10, it goes out and grabs it. If the next one's at point 30, it goes out and grabs it. It's not sequential. You don't have to go through 1 through 10 and then 11 through 29 to get to the next one. It goes out and the computer system, the CPU can go out there and directly address the RAM. RAM, you'll also see it referred to as dynamic RAM or DRAM. It needs to be constantly refreshed, so you got to have power on your computer system. There is a cycle that goes through, constantly refreshes the RAM. If power is interrupted, the computer's powered off, that RAM, data in that RAM disappears. RAM is made into these little boards here. We call them sticks, or dual inline memory modules. So remember that term, dual inline memory modules, or DIMM. Again, we may call them sticks also. Laptops use a version of a DIMM called a SODIMM, and a small outline DIMM, and that's a picture of a small outline DIMM versus the last one here, which is a regular DIMM. DIMMs are sometimes called sticks. Those metal tabs at the bottom of the memory modules are called pins. Different types of DIMMs have different number of pins, so they fit into different slots. The slots actually is a slot where they plug into, and those, you cannot mix the different types of memory into those slots. They are designed for a very specific type of memory. That notch at the bottom of the module matches a tab in the memory slot, so the memory prevents you from inserting it wrong, also prevents you from inserting the incorrect memory into the system. Don't try to force a memory module into a slot. You don't want to break these. If it doesn't fit, it doesn't fit. Now sometimes you buy the right memory, but you plug it in, you simply have to turn it around, and maybe this notice that slot's not centered, it's off center. So you're in there, you're putting memory in, it just doesn't seem to be going in. You turn it around and it slides right in. Again, don't force this. DIMMs have different capacities from 1 gig to 64 gig. Most PCs today use 8 and 16 gig modules. They usually also require you to install them in pairs. So if you have a 8 gigabytes of RAM in your system, you probably have 2 4 gig sticks. If you have 16 gigs, you might have 2 8 gigs or 4 gigs memory modules. Motherboards do require that all memories be the same type, and mixing different memory modules can cause errors. So don't try it. Just stay with the same memory module. When you buy a motherboard or a computer from, say, Dell or HP, it'll tell you what kind of memory you need. Stay with that kind of memory, and don't mix speeds. If they're all, memories have not only memory sizes, they have certain speeds, and you want to stay at the same speed with all of them, along with the same memory size. Random access memory has different types. Single data rate, which is now obsolete, and in this single data rate, its speed is synchronized with the system clock. Your single data rate RAM has 168 pins on your DIMM. Double data rate RAM can receive data at twice the clock rate. DDR RAM has 184 pins on a DIMM. Now there are different, as DDR1, there are different speed ratings, and as DDR gets bigger and faster and different capabilities, you'll get different speed ratings, and the new designs are always faster than the old ones. So we have DDR1 has 184 pins, DDR2 has 240 pins, DDR3 has 240 pins also, but that notch is in a different location. So remember, if you go if your motherboard specifies DDR2, you have to buy DDR2. DDR3 will not work. They both say 240 pins, but that notch is in a different location. DDR4 has 288 pins in a memory module. You might see the term SDRAM or DDR SDRAM. That S stands for synchronous. Now all RAM is synchronous, so SDRAM is the same as DRAM. So if you see a DDR SDRAM and a DDR DRAM, they're basically the same thing. The S is really not necessary, but for some reason manufacturers just started putting the S on there for whatever reason. This is not in your book, but you may encounter these also at different times. This is other types of memory in the system are read-only memory, programmable read-only memory, and erasable programmable read-only memory. This type of memory is used for system operations such as BIOS. It's non-volatile, so this is programmed at the manufacturing plant. It's an application, and it's installed into the system. All systems will have either ROM, PROM, or EPROM chips in them, and it's non-volatile. It's programmed at the manufacturing plant. You're not going to be able to change these. In a virtual environment, when you have remember we talked about virtual environments in Chapter 1, where you can have one computer system that's really big and it can run its own separate guest or host operating systems. When you install those guest operating systems, you have to specify virtual CPUs and the amount of RAM that the virtual machine is going to have. If the guest isn't performing properly, you can add RAM and add CPU to the virtual hardware. When you add that RAM or add that CPU, we call that scaling up. Removing it is called scaling down. That's called vertical scaling. So adding RAM or adding CPU to a virtual environment scales it up. Removing it scales it down. And that is, again, called virtual scaling. The reason we do virtual scaling is, we'll say you are running a retail store and you have a website. Throughout the year, one CPU and 64 gigabytes of RAM work just fine in the system. Christmas comes along and all of a sudden you're doing 4 times the business. So you might need to add RAM and CPU to keep up with the new demand. You add the RAM and CPU. When Christmas is over, you scale it back down. Motherboards are systems where it is a board that has all the electronics for the computer that all the memory and CPU and other chips plug into. On that motherboard will have electrical pathways that connect your CPU to memory, CPU to other I/O devices, and that pathway is called a bus. And all communication within the data occurs on that bus, and that bus is managed by the system's chipset. That chipset, ROM, PROM, or EPROM, is that chipset. Motherboards have different shapes and sizes. So if you go out and build a computer system, you have to match the motherboard with the case, and then once you've got your motherboard and case, you're going to get your CPU and memory that fit on that motherboard. Your most common form factors are ATX. These are large motherboards. They're used for very large desktops and tower PCs. The micro ATX is for smaller systems, and the mini ITX is a mini or really tiny motherboard used for very small or specialty systems. Motherboard features, it depends on what CPUs it will support. Will it support an Intel or an AMD CPU, and which model of CPU? The RAM configurations must match. Is it DDR3, DDR4? And the motherboard will have a minimum and a maximum amount of RAM. And that pairing I told you about with RAM, that will be specified in the motherboard. You need 2 sticks. Well, some of them might be able to handle 1 stick, but 2 sticks, 4 sticks. If they're going to handle more than one, they're going to be in at least pairs, sometimes in 4 or 8 at a time. So you're going to have to figure out how much RAM you're going to have to buy, and match it with the motherboard specifications. And then also built onto the motherboard will be some built-in components like an audio, video, and network cards. So again, if your system has an audio capability, it might be built into the motherboard. If it has video, it might be built in. Some people, when they build their systems, don't like the built-in audio, don't like the built-in video, may not like the built-in network, or they might like, they might like the network, might be acceptable with the audio and the video or not. So we can add to those, and we add to those using expansion slots. An expansion slot is just a slot within the motherboard where we can add different cards. And again, we'll talk about these cards again in the next chapter. The most common expansion slot we have today is the PCIe or the PCI Express. Our firmware is the last part of the motherboard. This is part of those ROM packages, ROM, PROM, or EEPROM. And this basically tells the computer how to boot up and what features it has installed at the hardware level. Where's your boot drive, are using encryption, that type of thing is all part of firmware. The two most common types of firmware you're going to see is Unified Extensible Firmware Interface, or UEFI. This is newer. It's been around for a few years now, but this is the most common one. If you're running Windows 11, you're going to be using a UEFI firmware. Basic I/O system, or BIOS, is an older one. Versions before Windows 11 can use BIOS, but Windows 11 does require UEFI. Special features such as storage and other controllers and encryption are all part of the motherboard. And again, depending on what features you want, may depend on what motherboard that you purchase. Last final thing we have here is our power supply. Our power supply unit is a metal box. We're talking desktop or tower here. It's usually located in the corner of a case somewhere. This PSU will have a power rating in watts. It's important that you know what your total system is going to be taking in terms of power. Your CPU is going to require power. Memory is going to require power. Hard drives require power. So you want your power supply to be beefy, to have enough power, to be beefy enough to supply everything without falling short. So know what your power ratings are on everything before you just swap out power supplies or buy a power supply. Coming out of the power supply unit are wire bundles that supply power to different components. So remember, the power supply converts AC 110 volts from our outlets to the DC required by our motherboards and other components. So you're going to be 12 volts DC, 5 volts, or 3.5 volts. The largest connector is a connector that connects to your motherboard. That's again that bundle, and it's a 20 or 24 wire connector that plugs into the motherboard. That's called a P1 or an ATX connector. This provides power to your CPU, RAM, and other components built into the motherboard. Some systems have an extra 12 volt connector called a P4 connector that attaches somewhere else in the motherboard. It's a really small connector. Some high-end motherboards require a P8 connector, not the P4. Laptops, they use a power brick to power the laptop. Power bricks are external to the laptop, and they might use a USB-C or other type of plug that plugs into the laptop. Again, the other part will plug into your standard wall jack. The power bricks also charge batteries along with providing power to your laptop. That's it for this chapter. Thank you. I'll have chapter 3 out there shortly.